Okay, so in this video we're going to go ahead and concern ourselves with the restricted free body problem. Alright, so to that end, let's go ahead and look at our three free bodies here. We'll put, say, M2 out over here somewhere. We'll put M1 over here somewhere. Then we'll put some smaller guy over there, M. Okay. So we'll go ahead and direct our coordinate system, X, Y. And it will make sense to tilt it along the M1, M2 line, like so, X prime, Y prime. And this doesn't necessarily have to be aligned along Y, so let me just move it off to the side a bit to make that more obvious. Okay, so we will say that we are a distance A away from center mass here, and a distance B away over there. And these are, so this is our center of mass, and the blue here are actually going to be a rotating coordinate system. Let me move my M2 just a little bit. I want it to be in line. Yeah, much better. Okay. There we go. So the blue coordinate system will be rotating around as the center of mass as M1 and M2 rotate about each other. And then M3 is just going to do whatever it does. So let's go ahead and call, let's pick another color here. Let's go ahead and call the distance from little m to the center of mass r prime in the primed coordinate system. And this would be r2 prime, and that in the rotating coordinate system would be r1 prime. Alright, so we can start by writing the external forces. The external forces will be minus, we can write this way, G times M1M over R1 prime squared. That's gravity there, and we need to construct a unit vector, so R1 prime over R1 prime for that, minus of G M2M over R2 prime squared, and construct the same kind of unit vector there, R2 prime over R2, like so. Alright, now we are in a rotating coordinate system, so that means we also have to include the fictitious forces. So this will equal ma prime, so this will equal the external forces minus 2m omega cross v prime minus m omega cross r. And we don't have to worry about the other two fictitious forces because A naught and omega dot are both 0. Alright. So let's work out the Coriolis acceleration here. So there'll be 2 omega cross v prime. That'll equal, when you take the cross product, you'll get 2 omega k prime hat. And we're crossing that with x dot I prime, oops, that's primed 2, plus y dot prime j hat prime. And so you take the cross product and you end up with minus 2 omega y dot prime I hat prime plus 2 omega x dot prime j hat prime. And then the centrifugal acceleration, remember, is going to just be omega cross v prime. Or sorry, r, I mean. R prime. So that will be omega times k hat prime, because we're rotating about in the xy plane, so omega points along in z. And we're going to cross that into omega k hat prime, and we'll cross that into x prime I hat prime plus y prime j hat prime. And when you do, you get omega squared x prime I hat prime minus omega squared y prime j hat prime. Okay. So we can, while we're at it, let's go ahead and write our F over m for the gravitational forces. So we get like a gm1 over r1 prime squared times r1 prime over r1 prime. And then same deal here, gm2 over r2 prime squared r2 prime over r2. Dropped a minus sign there. All right, so you can work that out, and you're going to get that to be a gm1 over x prime minus a squared plus y squared for the distance. And then we need to take the, and here I'm just taking the x component. So that will give me x prime minus a over the hypotenuse, x prime minus a squared plus y prime squared, minus gm2 over x prime plus b squared plus y squared. And that component will be x prime plus b over root x prime plus b squared plus y prime squared. Awesome. And then there will be a similar, okay, so we have the x term, and then there will be a similar term for y that I lack the energy to write. So now that gives us the x component of the acceleration is this bit from the physical forces, and then we have to add in from the fictitious forces a plus omega squared x prime plus 2 omega y dot prime. Similarly, y double dot prime will equal minus gm1, and then this will be a y prime over that same gobbledygook minus gm2, and then this will be an x prime plus b over that same gobbledygook. Plus omega squared y prime plus, minus from the fictitious forces minus 2 omega x dot prime. And in general, this is a mess, and you can only solve it numerically. But we can go ahead and take a look at it, say in case where the objects are really different in mass compared to each other. So say like the Sun to Jupiter, and then Jupiter to just some asteroid or something like that. And that would correspond to what are called the Lagrangian points. And the book does a really good job of treating this using effective potentials. And I certainly invite you to read and understand that. But I want to just take a little more two-fingered approach here, as one of my old professors would say. So let's go ahead and draw in our solar system. So there's the sun, mass M1. Out over here somewhere is Jupiter, mass M2. And then the 5 points where our asteroid will orbit the sun at the same rate as Jupiter are the 5 Lagrange points, and they are located here. This is L1. There, that's L2. Somewhere over here, that's L3. These are all in a line. And then if I go and complete an equilateral triangle, both up and down, so all these angles are 60 degrees. This is L4. Oops, let me go back to the same thickness there. There we go. This is L4. Oops. Doggone it. 60 degrees. There. And then this is L4, and that is L5. The text's labels in figure 7.44 are erroneous. This is correct. Okay, so anyway, at any of these Lagrange points here, whoops, the velocity in the center mass system is 0. They're just seen as stationary. All right, so let's go ahead and examine this now in the frame of the sun. And it'll turn out we'll have to do 4 analyses. The analysis for L4 and L5 are the same. But let's start by taking a look at L1. So here I'm rotating it 90 degrees from how I had it drawn over there. Alright, there's a very badly drawn sun. There, that's much better. So M1, Jupiter's out over here somewhere, that's M2, and our asteroid is out over here at L1. We'll call this distance big R, and that distance little r. So if we go and look at Jupiter here, from Kepler's third law, we can write that t squared equals 4 pi squared over g. And remember, we have to have the mass of the sun plus the mass of Jupiter added together, times r cubed. Now let's go and look at so this is for Jupiter. Now let's go ahead and look at some asteroid sitting at L1. The force, it'll be feeling an attractive force from the sun, and we'll put sunward as positive because we're going to orbit the sun. This will be gm1 times the mass of the asteroid over r minus r squared. And then Jupiter's going to be pulling it the other way, minus gm2m over r squared. And that will have to equal mv squared over r minus r, which will be the radius of its orbit. Okay. So we can cancel little m's everywhere. And we can recognize that the speed here has to be 2 pi times this radius divided by the period of the orbit. So we're assuming it's a circular orbit. If you want to do this for ellipses, go right ahead. Just so we have Jupiter's circular enough anyway. So gm1 times r minus r squared minus gm2 over r squared equals, so we have here a 2 pi r minus r squared over t squared. Divided through by r minus r. Now it'll be helpful here to multiply both sides through by r minus r, like so. So at the Lagrange point, though, the period is the same as the period from Kepler's harmonic law for Jupiter. So we're just going to plug that right in. So now we're down to gm1 over r minus r minus gm2 r minus r over r squared equals, okay, squaring this at 4 pi squared r minus r squared over 4 pi squared over gm1 r cubed, little r cubed. Okay, so small favors there. We can cancel the 4 pi's like that. And this is 1 over g, so we can cancel the g's too. Life's good. And we can clean this up a little bit. We get m1 over r minus r minus m2 times r minus r over r squared equals, I'm sorry, this should be m1 plus m2 here. Equals m1 plus m2 times r minus r squared over little r cubed. Now, if you play for this, we need to solve this for big R. And unfortunately, this is a quintic in R. And it's been proven that there is no general analytic solution for a quintic in anything. But you can always solve it numerically. And for Jupiter, when you do solve it numerically, you get that big R is approximately 0.067 little r. So 6.7% of the Earth-Sun distance. All right, so we can repeat the analysis for point L2. So Sun, Jupiter, then here's L2 hanging out over there. So then this will be R, that will be big R, like so. And this is still M1, that's M2. So again, you can write the force law, and that'll be Gm1m over R plus R squared plus Gm2m over big R squared. So we have a sign change here and a sign change there. I will save you the tedious algebra and get m1 over r plus m2 times r plus r over r squared equals m1 plus m2 times r plus r squared over r cubed. And again, it's a quintic in big R. And for Jupiter, big R is approximately 0.070 little r. So a little further out than it is for L1. Okay. For L3, that one's on the opposite side of the sun. So this is Jupiter here, and I'm going to kind of mark off a little bit of its orbit there. Then we got the sun sitting there. Distance, little r. Then here's the other side of Jupiter's orbit there. Then there's L3 over here. And then that distance there is big R. Now the idea here is that Jupiter and the Sun are conspiring both to pull an asteroid here together. And so although you're further away, you have a bigger effective mass, if you will. And so you'll still orbit with the same period. So you can go ahead and write the forces here. You'll get, this is G m1 m over r plus r squared plus g m2 m over 2r plus r squared equals mv squared over r plus r. And doing the same tricks we did before, this is going to turn into m1 over r plus m2 r plus r over 2r plus r equals m1 plus m2 r plus r squared over r cubed. Again, you get a quintic in big R. And for Jupiter, big R is approximately negative 0.00024 R. So the actual Lagrange point sits just inside over there somewhere. Just inside. All right, so drilling, we can treat L4 and L5 simultaneously. So I'll just do L5, it doesn't matter. So we're going to have us an equilateral triangle here. M1. Those are all supposed to be 60 degrees. I tried. Okay, so we got Jupiter out at this vertex here, M2. And then since I drew the one on top, that must make it L5. All right, so if we look at the forces acting on these, I'm asserting that at this point here, there's my F1, there's my F2, I'm asserting that the net force points to the center of mass. Right there. All right, so let's see if that's actually true. So I'm claiming the net force points to the center of mass. So if that's the case, it'll orbit the same common center of mass at least. And then I'll have to work on showing the periods the same. So in order for that to be the case, let's dimension out some angles here. We'll call this L1 alpha. We'll call that one beta. So we need that alpha plus beta equals 60 degrees. So if we go ahead and actually add our vectors together like so, this will be F1. There's going to be my F net like so. And that angle has to be alpha if it goes along that line. So this will be F2. We follow our geometric constructions. This will have to be beta. And since alpha plus beta equals 60, that forces this to be 120 degrees. So we want to show this. If we do that, we're golden. All right, so we'll call this distance here B, and that's A. We'll call that big R. We'll call this little r. Okay then, which will be the same for both legs of the triangle because it's an equilateral triangle. So force F1 is equal to Gm1m over r squared, and similarly F2 is equal to Gm2m over r squared. Now I need the bits of F1 and F2 that are perpendicular to r to cancel. So that cancellation condition requires that F1 sine alpha equal F2 sine beta. We'll call this guy star. We're going to need him later. So if this is true, then we've got that our forces point to the center of mass, and then we're all happy. So putting in what the forces are, whoops, this is Gm1m over r squared sine alpha equals Gm2m over r squared sine beta. Cancel, 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 cancel where we can get it. All right, so we have m1 sine alpha equals m2 sine beta. Now, the center of mass, in order for the teeter-totter to balance at the center of mass, it has to be the case that m1 times a is equal to m2 times b. So we'll divide here through by m1a, and what that's equal to there, m2b. Cancel, 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 cancel. And then I go and look at this and say, oh, hey, this angle here was beta, right? Okay. But more importantly, this angle here is beta. And so sure enough, we're recovering the law of sines. Sine alpha over alpha equals sine beta over beta. And so that tells me retrospectively, since I know this statement is true, that tells me retrospectively that star is true. Okay. So now that I know that that is true, I can go about showing that the period for somebody at L5 is the same as at Jupiter. So the components directed towards the center of mass are going to be F1 cosine alpha plus F2 cosine beta. And that'll equal m times 2 pi r squared over quantity squared over r. Divide that by t squared. Okay, that's just v squared there. And this is, so that makes that mv squared over r. We'll put in the forces for what they are. Gm1m over r squared cos alpha plus Gm2m over r squared cos beta equals m times 4 pi squared r over t squared. Okay, cancel, 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 taking it where we can get it. All right, so I need to rearrange this for t squared. So t squared is equal to 4 pi squared r squared over g times m1 cos alpha plus m2 cos beta. All right, now let's meditate on this for just a quick moment here. Capital R here is going to be equal to big R, little r here is equal to, let me rephrase this, capital R here is equal to little r times the cosine of alpha, or it's equal to little r times the cosine of beta. So the one thing we know is that the cosine of alpha and cosine of beta have to be the same. So that's at least something. All right. So if I go ahead and put in for that, I can now group this out, right? And I can observe that r is equal to little r cos alpha. So I get t squared equals 4 pi squared r cubed cos alpha over g m1 plus m2 cos alpha. Those annoying cos alphas cancel. And I wind up getting Kepler's third for Jupiter. So that means that somebody at L4 or L5 has to orbit around the Sun with the same period as Jupiter. Okay then, in the next video we're going to go ahead and play with some computer sims for a bit and look at the Kirkwood gaps. These are places where Jupiter's gravitational influence ejects asteroids.